Thank you, everyone. Thank you very much to come to the talk, and thanks for the Science for Georgia to give me the opportunities to present one of my research, which is bendable concrete. So the bendable concrete for the next generation civil infrastructures, safety and durability. So throughout the whole presentation, you will see that the bendable concrete actually named as Engineered Cementitious Composite. That's the official name of it. So in short, ECC. Just be aware of that. So before I go talk to ECC, I'm going to share a little bit more about myself, the path of my professional experiences from a civil engineer to a concrete material scientist. So I was a civil engineer and a structure engineer back to Hong Kong, and I decided after several years of working, I decided to go back to school, and I got my master's from University of Michigan. And recently I got my PhDs from Georgia Tech, and now I'm a postdoc at Georgia Tech. In the future, and since now we are facing the coronavirus and everything, so I don't know what my future looks like, but hopefully I will be a professor. So every time when I meet someone new, and they always, the first thing I introduce myself, I'm a civil engineer, or I'm a civil engineering student. So they always ask, what is civil engineer? So I think that's be interesting. So I put up several of the pictures. So what is a civil engineer? What does a civil engineer do? So people have all sorts of the expectations. My friends think that I'm a fancy guy that see, tall high-rise buildings goes up. My parents would think that I am a scientist that build a very advanced technology. The society and the boss may think that I'm just goofing around. So when I grow up, I actually know these pictures. There's people sitting on this high-rise steel structure in Chicago all the time. And I really liked it. I thought that's what my imagination, that's how I would imagine myself to do in the future. I just got these pictures. The person sleep on the structure drawings yesterday, and I was like, is this what we really do? So sometimes it's true because we always overtime for a little bit every week, and we were so tired. But my passion and my motivation to be a civil engineer is actually originated when I was a child. I always fenced these ancient civil infrastructures. And luckily, I got opportunities to go around the world and see those ancient civil infrastructures. Taj Mahal in India, Machu Picchu in Peru, Great Wall in China, Colosseum in Italy, and Chichen Itza in Mexico. So I got those opportunities, and I was always fancying that how these infrastructures can sit for thousands of years and never actually collapse. So that is one thing we learn from others. And then I'm from Hong Kong. So in Hong Kong, I face all of these tall buildings, these modern infrastructures. So Hong Kong is basically a concrete forest. You see that all the buildings are like 50, 60 floor. And this is actually the view, the Victoria Harbour view from a peak, the mountain, the top of the mountain from in Hong Kong. And you see how condensed and the impact of those. So when I was back in Hong Kong, my last job was to design a casino and a hotel resort, which is MGM. So this is one of this casino project. It's very large, and I was lucky to be the project engineer of that. And the construction cost alone is $3.4 billion, and the overall development is more than 4 million square feet. So think about that. And this is one of the model I designed. I would like to share here with you. It's just bending all the time. It's exaggerate a little bit, and it's not the real under the wing load. So that is what I did before I went back to school. So today the talk, I'm going to tell you what are the motivation and introductions of why I get into the concrete materials from the structure and the civil engineers. And then I will talk the main course is bendable concrete, the properties of bendable concrete, and how bendable concrete is more advanced than the conventional concrete. And then last, I will introduce how this bendable concrete has been used or applied to different industrial applications. So first, what's the motivation? Why we care about the concrete infrastructure or concrete? So first, let's say the worldwide urbanization, and you see that this urban growth per hour. Every city you see that we have 20 or 50, 60 people, so it grows every hour in Asia, South America, Africa. You see all around. And with such increase of world urbanizations, and you know that like Mexico City is now 20 million people in the city, and Tokyo has more than, I think, is 100 million people over there. So to accommodate those such amount of people and the population and also the worldwide urbanizations, we have to build. So there is ever increasing infrastructures, and you see that all the tall buildings that people accommodate, from the Kingdom Towers in Abu Dhabi and the Sand of in Singapore, we have all kinds of tall buildings. And in addition to the buildings, we even have the more infrastructure bridges. The one on the left side is this one is the Macau-Zhuhai Bridge in Hong Kong, and it is connecting Hong Kong to Zhuhai City. The bridge itself is across the sea for 35 miles. So you have to spend like 1 hour in this driving across the sea over there. And this is a dam in Brazil, and one of the things that help us to have these electricities and everything. And the last one is complex infrastructure, or the highway infrastructures in Dallas, Texas. So to do that, to able to achieve that, we have to make a lot of concrete. So that's why we care about concrete. So you see that concrete productions, or the cementitious based productions, it's increased exponentially for the last decade. And annual concrete production is around 12 billion tons, which is equivalent to 2 tons per person per year. That's a lot. Everyone is responsible for 2 tons of concrete. And concrete is the second most widely consumed material, second only to water. So water is very important. It's very critical life materials. We cannot live without water, same as concrete. With such a scale that we know that if we can do a little bit improvement to concrete, we have a huge, tremendous impact on the society. But does the concrete is perfect? Is concrete now like we can use? We have been using concrete for decades, but it's not perfect. So why is that? What the problem is? So concrete, we know that it's very, very strong in compression. So we put into as a columns. You see all the buildings columns is made by concrete. It's very strong. But once it's under tension, such as bending, like you put a very heavy shelf in the room and the beam underneath is under bending, or the truck is crossing the bridge, it's under bending. So the bending is under tension and a stretching load. So once it's under tension and stretching load, it's no longer as strong as in compression. So it cracks. And once it cracks, oxygens, chlorides, and moisture just goes through those cracks. And it masks those chemicals and those waters, it mess up with the reinforcement underneath, and then cause a corrosion of the reinforcement. And the corrosion product push out the concrete cover and has a concrete spalling. So that's what we usually see in the real world. That's how concrete spalling and the corrosion of reinforced concrete looks like. By that stage, we have to go for the repair. So we have always go to repair, and you know that I always drive through North Side Drive from my place to Georgia Tech campus, and it's under the repair all the time since 2016 I came here. So with such repair, you have to produce new materials. So the concrete production is actually responsible for 6% of greenhouse gases. And producing 1 ton of concrete and also produce 1 ton of carbon dioxide. This is not good. All of this creates durabilities and sustainability concerns for the current concrete infrastructure. And in addition to that also those brittleness of concrete is also created safety concerns, especially when it's facing the concrete infrastructure is facing nature disasters. In 2008, the Sichuan earthquake in China, and you see the mother was crying for losing the child. And the Fukushima nuclear meltdown in Japan, that actually was the pollution, this nuclear pollution polluted the Pacific Ocean. And in 2017, the Hurricane Maria hit Puerto Rico. Hundreds of thousands of people died from there. That's not good. That's definitely not good. So the current grade of concrete infrastructure in the United States is D+. Obviously not good at all. And I don't think anyone, the students or the parents of children, don't want their grade is D+. So in order to improve and increase the grades, National Academy of Engineers have proposed 14 different grand challenges. One of them is a very important one, that is restore and improve urban infrastructures. So to do that, I believe, and I think bendable concrete is a future and is a solution. Again, bendable concrete is known as ECC, is Engineered Cementitious Composite. So what is this one is special? How this compare to this conventional concrete or fiber reinforced concrete? The conventional concrete is brittle. It breaks like glass. When you have the bending, it just breaks into half. So you see the deformation actually is quite low compared to others. With a little bit loading, it just breaks to half. And then people put fibers into the concrete. So the fiber reinforced concrete, it helps, of course it helps. But it still has a localized crack. And you see that the crack was just centered and it was delayed by bridging, fiber bridging. So it, of course, it has some deformation, but at the same time, the load cannot sustain. So to improve that, we have the ECC that has multiple fine crackings. Not only it has a large deformation, it maintains a load at a certain level. So with that, we have the typical ECC, features and the direct tension. And first of all, this is a sample that and the direct tensions at the both sides. And you see that the deformation can go to 5%. And compared to normal concrete is 0.1 to 0.2%. So the tensile ductility, all we call that the deformation capacities, all the deformation capacity goes to 300 times of the normal concrete. And throughout this deformation, and we formed microcracks with crack width less than 100 microns. So give a sense of what 100 micron actually means. Is the thickness of your hair is 100 microns. So you see the crack on this picture, the thickness of each crack is actually thinner than the human hair. So with such a thin cracks or very excellent controlled cracks, you can improve the durability of the concrete, of the bendable concrete. So again, you see that with the compare with the penny, that the microcracks is very, very fine. And we know that we did a water penetration because water was one of the causing factors to mess up the concrete, the reinforced concrete. So you can see the ECC and compared to non-crack concrete, it has the same water permeability, so it's very tight. But once the concrete was cracked, especially before the AASHTO's limit, so the AASHTO is a federal highways requirement for the cracks. It's about 300 microns, so like the thickness of 3 hairs side by side, and you see the permeability goes to like thousands and hundreds of thousands times more. So it's about 4 or 5 magnitude compared to non-cracked ones. So the thin microcrack improves the durabilities of ECC. And additionally, that thin crack also, because of large tensile ductilities and deform capacities, it also improves the damage tolerance. And you see the plain crack, when this crack, this has again formed a single crack. You see from the left side of the image. But once you add an ECC layer, this part is the ECC layer. Once you add it, you can rest the single large cracks from the up nearest concrete. So this part is concrete. And it diffused to multiple small crackings. And because of the multiple small crackings, it can against and protect the concrete underneath and help lower the water penetration. So with such a kind of superb performance, what's the difference? the material component, is it different from other concrete? Actually, it's slightly different. So normal concrete, we don't use fibers, but for fiber reinforced concrete, we use it. So it's not that much. And the solid is basically the same as a normal concrete. We use cement, silica sand, and fly ash. And the combination of them. So can we just mix all of them like when you're making cake and produce ECC, like at home? Actually, no, you have to design ECC. So the ECC design philosophies is from the fiber coating, the fiber treatment, to understand the interactions between fibers and also the cement basis matrix. And then you know the fiber bridging properties, and they go all the way up to the composite properties and the structure element, and it goes to the structures. So to design that, we have to understand the micromechanics. Today, I'm not going to talk about micromechanics. You have to take a class for that. But I will talk a little bit about the historical notes for developing ECC. So ECC was first developed by Professor Victor Lee. Now, he is James Wright's Distinguished University Professor at the University of Michigan. He was my supervisor of my master's degree. And he invented ECC and uses micromechanics models to tailor the ECC for different type of applications. And one of his early students, I think was second student, Christopher Learn, he was my supervisor back to Hong Kong when I was an undergrad. This professor, he's a professor at the Hong Kong University of Science and Technology, and he and Professor Lee developed the first generation of ECC materials. And their development was 1992, very early time. So after the first generation of ECC, it has been throughout the world, especially in Japan, because it's on the earthquake zone due to such a superb performance. And Japan has been using this type of technology for a long time. And members including not only the academia, but also the industry and the government organizations. And all of them conduct research, development, and also the commercialization of ECC technology. And recently, we added 2 more members of that. One is UC Berkeley and Georgia Tech. We had collaborations with Victor Lee from University of Michigan. And how we designed that, the recent approach is we use polo material from UC Berkeley, and he is a real Carlson Distinguished Professor and also the member of National Academy of Engineers. And he used advanced materials characterization technologies and techniques to understand the fiber behavior in ECC, so we can better tailor this fiber behavior rather than go to use a lot of trial and errors. And my PhD supervisor, Kimberly Curtis, and he's a professor and associate dean at Georgia Tech. We want to use alternative cementitious materials to further improve the ECC performance and also at the same time reduce its cost. So before I go for the second ones, I want to share a little bit my relationship with those ECC group members. At that time, we was have a project meetings in University of Michigan with Professor Lee, Professor Materials, and Professor Curtis, and also my older professor when we had meetings in Hong Kong, Professor Learn and Professor Lee. So with that, I want to go to the bendable concrete. So we now know why do we care about bendable concrete and how the bendable concrete was actually historically developed. So what properties or functionalities the bendable concrete actually have? So first, concrete has a self-healing functionalities. So by this self-healing, I want to show you a video, very quick video first, and see, and you have some ideas what this actually means. So that is a crack. After several times of cycling with water and the carbon dioxide, it self-heals. So pretty much like a paper cut on your finger. So I want to ask the audience, later we can discuss about that. What do ECC features enable such self-healing properties? Why it self-heals? So again, that I just said this has a very fine crack, right? So I believe everyone has experienced the paper cut on the finger. So once you have a paper cut on the finger, you never actually need to go any hospitals to treat it. It's just a self-heals. So because of such a fine crack like a paper cut, it can self-heal. So it's like a Wolverine, it self-heals all the time. But compared to normal concrete breaks in half. So with this paper cut knowledge, that it's normal concrete is more like you cut or you chop your hands off. And there's no way that you can self-heal without external surgery. So that's why, in summary, that ECC can enable the self-healing is fine crack. The fine crack is one of the key elements that is cracks. It can self-heal. So what other functionalities or properties it has? So it has impact resistance. Again, I want to show you a video of what means high impact resistance. So this is a concrete. So we drop some very heavy machines on the concrete. It shatters into pieces. It's very obvious because it's heavy and it's impact load. But for ECC, the similar drop and the same drop and the same load, they barely have a dent. So such impact resistance, and you can see that the large impact energy can be absorbed from the ECC. On the surface, the front side is under compression, and actually nothing happens. On the back side, again, it not shatters, it just forms fine cracks and then remains integrity. And such property can be used for high-risk buildings, and especially against those attacks and nature disasters. So with that, we have other functionalities. What else do we have? We have the fatigue resistance. And the fatigue resistance and means you can see in this picture. The first one is reinforced concrete. After the earthquake load, it just drops, all the concrete was shatters and then lost their capacity. And for reinforced ECC, after very large earthquake load, it still remains its integrity. And we have tried to build one of the columns and to see what happens in this real simulation of that. So again, that's columns. You have the reinforced concrete on the left, which has a bounce splitting and a spotting of the cover. And this load is basically you have the load and shake that. And compared to this material strength, concrete, we built this concrete deliberately higher material, like 25% higher than the normal ECC. But as a result, the panel structure strength actually is higher. So with lower strength materials, we actually build higher strength concrete panels. So that's how well that material strength cannot directly represent the structure strength if they have other properties. So that this is a fatigue resistance. Also, we have a self-sensing. And how we make those self-sensings, why do we care about self-sensing? So we already know the self-healing. So it's basically you have a paper cut on your finger. But you want to know which finger you had a paper cut. You don't want to know, I have a paper cut on the finger, but I don't know which one. So the self-sensing is more like an ouch moment that you know where the hit happens. And by doing so, you just change, because of the crack formation of the cracks, ECC's resistivities or the conductivities, the electrical properties change. And such change you can see from here that from noun cracks, the noun crack A and B, the very few crack noun cracks, it basically has it's very, very low resistivities. And once you have more cracks at H, the resistivity goes up. So that's how you understand. And to translate such kind of ideas to real laboratory, and you can see that with this one, with the concrete crack forms here, and you understand there is some image analysis. And then by the end, you see that the cracks and represent this one. So in this way, you don't have to go to the site to monitor or observe the concrete infrastructure. It will tell you where exactly this problem is, and you can go to repair that. So this is self-healing, self-sensing properties. And then the sprayability. Why sprayability is important? So in Hong Kong or New York or Tokyo or London, they have a lot of tall buildings. And tall buildings are built for like several decades ago, and that has problems for concrete spalling due to this deterioration of reinforcement. And this is dangerous to pedestrian. If you have a chunk of concrete falls off from the tall buildings, you may kill someone. So in order to prevent that, in Hong Kong, we propose some ideas to put a layer of, or spray a layer of ECC on the top of that, so it can prevent concrete spall. And that is a conceptual illustrations. And let's take a look of the lab test. So you see that after even this concrete drops, it's basically 3 blocks. It drops, the ECC can still maintain that, and then we apply one on the wall. But once it bulges, if you see the ECC cover its bulges, and you know that, oh, there must be some problems over there, you can have to go to repair. So this is one of the things that can prevent the safeties, prevent the concrete fallings from high-rise building. And lastly, it has self-cleaning properties. So what I mean by self-cleaning? So self-clean is when you see those ones. This one is with titanium dioxide. So by using titanium dioxide, you can clean the surface of concrete. This one is without titanium dioxide. So those are the chemical and also the organic dye. And when you do under the titanium dioxide under the UV light, which is from the sun, you can digest those dirts and it can just die down to 0. So it has been applied to several infrastructures in Europe. The Jubilee Church uses this titanium dioxide to self-clean the surface and able to achieve a clean look all the time. And in addition to that, titanium dioxide can also break down NOx. So NOx is a combination of nitrogen oxide and nitrogen dioxide. It's basically from your car. So once you have these pollutions, if you see a large area like Atlanta or Los Angeles, you see those pollutions, you have the fog, you cannot really see the buildings from far away, and because of the NOx. And using titanium dioxide, you basically can break down NOx into nitride and nitrate, and this can bind with cementitious component, and then hence air purified in this one. So in this way, we understand that ECC has several superb properties. So what has been applied into the real infrastructures? So we're always talking about the smart cities in recent decades, smart cities. So how this ECC can contribute to the next generation infrastructures as well as the smart cities. So here I want to give 4 examples: the wind tower, the tall buildings, the pavement, and the link slab. So first, let's go to take a look at the wind towers. So again, renewable energy is the future of the future of us. And you see the United States or North America, the growth of the renewable or wind towers has been obvious. It grows larger and larger and tall. We're talking about 200 meters in the future. It's taller than Washington Monument. So in order to achieve that, we proposed the idea of using ECC as protective layer for tall concrete towers. So this is towers, and we have one of the layers outside. So why this layer outside is helping for this one? I did some of experimental approach. So again, this is one of the things. You have 2 layers, a 3-inch layer of concrete. So we have the concrete core of the wind turbine towers, and then we have the ECC 1-inch protected layer. This is just a representation of the real infrastructure. And in this case, again, as I showed before, that the major crack in concrete can be arrested, and a single crack in concrete and diffused into multiple crackings. Again, multiple cracking is fine and protect the inside concrete from those aggressive chemicals and other things. And this concrete towers can also be prefabricated and assembled on site. And you see this ECC protective layer, the concrete core can just make it in the prefabrication concrete manufacture, and then just connect the segment and stack to each other on site. And this one, because of this idea, and I also developed the strategic use of ECC as a permanent formwork. So what I mean by permanent formwork? So the formwork you can live into this construction forever. You don't have to take it away. I think many people may have some questions. What is a formwork? So that is a formwork. The wood, those woods is a formwork, like you can see from here. And the building a formwork for these things requires a large amount of labor, and often it cannot be reused. You have to throw them away. So it's a huge cost if we can use ECC as a permanent formwork and also as a structure member that can improve the durability. So the second case is tall buildings. So ECC for tall buildings, we have 3 tall buildings actually have involved ECC applications. The 20-story Gloro Towers in Tokyo, 41-story Nabulu Towers in Tokyo, and another 60th-floor Kitahama Towers in Osaka. So 3 of the towers, why this is important? Because Japan is on the earthquake zone. So using ECC coupling beams actually is helping this earthquake resistance. You can see this massive, coupling beams has been built in the manufacturers and then put into this one. So by using that, we can remove the super beam and damping systems from the original design of these tall buildings in Japan. And those systems, those big steel member systems, cost millions of dollars. But by replacing by ECC beam, it's much more ductile and more resistance to the earthquake, and also save the cost. And the end result is this building survives the 2011 Tohoku earthquake and the tsunami. This is one of the great demonstration of how ECC can be used in this building infrastructures. For the case 3, that we have the ECC for the pavement, and this is one of the pavement, the bridge in Michigan, M14, and we built 2 type of things side by side, ECC batch and the concrete batch, to see what the performance and the exactly same loading conditions and the environmental conditions. So the field verifications, after 2 days, you see that the crack already forms in the concrete batches, even after 2 days. ECC, of course, no visible crackings even under this heavy truck load. And we monitor this throughout the time for 2,000 days, almost 4 or 5 years. And you see the concrete patch has been so shattered, and it had to replace the whole bridge in 2005. And at the same time, ECC barely have any crack width. It maintains for 2,000 days. So that is the beauty of that we can use it as a bridge in the future for this smart and self-heals pavement. And the final case is ECC's link slab. Why I talk about link slab? Because when we build the constructions, we cannot build a very long bridge. We have to build a segment by segment. And in order to build a segment by segment, and the conventional way is we have this expansion joint. You can see from here, and this expansion joint you can see everywhere. If you drive from here downtown to airport, you see a lot of bridges overhead and has an expansion joint, and you can see from underneath that all the steel supporting areas is corroded because the water and everything goes through those cracks. So in order to prevent that, we built this ECC expansion joint instead. So ECC link slab instead. So ECC link slab, once it shows the same thing. If it's under tension, it just goes up, and it forms small cracks. If it's under compression, the crack will just close. So under these conditions, it largely prevented the corrosions underneath the steel bridge girders and the stuff, and improve the durabilities of the bridge. And to demonstrate this performance, we also carried out a life cycle analysis. So comparing the ECC link slab versus the conventional joints. And this life cycle analysis, even though the ECC link slab is a little bit more costly at the beginning, but it has much more environmental friendly performance. And you can see that in ECC link slab shows lower energy consumptions and the carbon dioxide emissions due to this less repair events or the disruption of traffic. So mainly one of the large contribution for energy and the carbon emission is the traffic. Because you have to block the road for the repair events, the traffic has detoured and has to produce a lot of energy and the carbon dioxide. So with that, I conclude the 4 cases of that. And then the people asking me when I did this presentation previously, they always ask it, so it's super good. It's always so good. So what is drawbacks of that? Does ECC has any disadvantages? Actually, yes, it does. And it has the challenges for using ECC in the future infrastructures. So first, it requires the policymakers' promotion approval, because it's new materials and people are worried that maybe it has some side effect that other people may not notice before. And second, even though the current version of ECC is 2 to 3 times more than the conventional concrete, so it's very expensive. A lot of owners, like Department of Transportations and the building owners, they don't really want to put a lot of upfront cost to make the buildings or bridges with ECC. So that is one thing that we have to be focused on. And also, again, the more pilot projects are needed for demonstration of such performance and give the public more reassurance. So in order to do that, we have, I think, all of the following policy-making institutions, American Concrete Institutions, ASTM, American Standard Testing and Materials, EPA, Department of Transportations and Department of Energies, all of those policymakers have contributed to that. They have tried to see how these advanced materials can be used in their projects, and they have funded many researchers in the United States. And to reduce the cost of ECC, we have different ways, and one of the very direct way is to replace expensive materials, such as fiber and cement. So the fiber we use are polymer fibers, and now if we can use nature fibers from bamboo or from trees, that could be tremendously reduce the cost of that. And recently, we also find that the limestone calcite clay cement is cheaper than the production of the cement. So if we can replace those cement even partially, we can make the ECC a new version of ECC that is comparable to the normal concrete in cost. So more demonstrations. I think 3D printing ECC is a lot of attractions. This is one of the conceptual ideas how to print the houses that you can use this as emergency houses for, let's say, disaster areas. And also one of this demonstration in China that the people has 3D printed the ECC bridge cross over the river, and it's very strong and can be used. I think this 3D printing ideas can be used even for the future as space colonization, that we can print something out space, and it's strong enough that we don't need any reinforcement. So I wanted to show you one thing before I conclude this presentation. This is one of the videos we make in the 3D printing cementitious materials. And you see how this 3D printing actually means. When you print this cementitious materials, it goes up. It stands itself and not collapse. So this is one of the beauty of how you can actually use the 3D printing for the future infrastructure. So by that, I want to conclude my presentation with Bendable Concrete for next generation of infrastructures with such a tremendous, superb performance, self-healings, impact resistance, fatigue resistance, self-sensing, sprayabilities, and self-cleanings. We're hoping that this can be used for the more durable and sustainable and resilient next generation infrastructures. So thank you very much, and this is the end of my presentation.